the billion-dollar satellite that will trap humanity on Earth. The sky is falling. The collision came without warning. Two objects, one alive with transmissions, the other long dead, met above the Pacific at 28,000 kilometers an hour. In silence, metal tore apart. Thousands of fragments burst outward, each faster than a bullet, impossible to track, unstoppable once free. Within minutes, nearby satellites fired their thrusters in panic, warning lights washing control rooms in red. Operators watched helplessly as their screens filled with flashing arcs, debris spreading like an invisible storm around the planet. That single impact wasn't just another malfunction. It was the moment orbit itself, the highway circling our world, turned hostile. Fragments from the shattered Starlink unit ripped through lower lanes, forcing communications satellites into frantic evasions. Each swerve burned fuel, shortening lifespans. One skipped calculation, and the domino chain would begin, a runaway multiplication of collisions. The nightmare scientists warned about for decades was no longer theory, it had started. To see how we arrived here, rewind 50 years. When the first artificial satellites were hurled into the clean dark above Earth, orbital traffic sounded like fiction. Every nation wanted a slice of the sky, first as Cold War theater, later as infrastructure. The race that began with Sputnik never actually stopped. It just swapped flags for company logos. The goal changed from dominance to connection, unlimited communication, profit measured in data instead of prestige. Somewhere between ambition and convenience, we turned Earth's orbit into a junkyard. Above us now, nearly 500,000 fragments loop endlessly, including 36,000 large enough to obliterate a working spacecraft. Each obeys only physics, no brakes, no borders. Every launch adds to a crowd no one truly governs. For years it felt harmless. Space was big, collisions rare. But the odds have caught up. The Starlink loss after a geomagnetic storm exposed how fragile the system really is. A solar flare from 100 million kilometers away swelled Earth's upper atmosphere, slowing dozens of satellites until gravity dragged them down. 40 burned up that week. Multiply that by 1,000, and you begin to see how close humanity sits to locking itself beneath its own machines. And here's the question that keeps astronomers awake. What happens when space becomes too dangerous to reach? If one collision breeds 10, and each of those scatters thousands more, then low Earth orbit, the layer carrying weather, GPS, and global internet, turns into a cloud of lethal shrapnel. Launching through it would be like firing a needle through a blizzard of knives. The irony is sharp. The satellites meant to connect us may be the very ones that isolate us forever. Picture a clear blue sky you can no longer cross. That's the horizon this collision points toward, the moment human progress turns inward. We built a net around our planet, not to catch the stars, but to trap ourselves beneath them. The race to own the sky. In the beginning, space wasn't a marketplace. It was a proving ground. The first object humanity ever placed beyond Earth's atmosphere wasn't built for communication or profit. It was built to make a statement. When the Soviet Union launched Sputnik 1 in 1957, its steady radio beeps echoed across the world like a heartbeat from a new frontier. For the United States, those beeps sounded less like progress and more like a warning. Within months, the space race was on. A technological arms race fought above the clouds. Early satellites were few and precious. The US answered Sputnik with Explorer 1, and suddenly orbit became a domain for political theater. Each successful launch meant prestige, each failure humiliation. And because nations kept pushing, success piled on success. But so did the leftovers, used rocket boosters, dead satellites, and fragments from early tests that never came home. Nobody thought much about debris. Orbit seemed endless, the sky vast enough that a little clutter couldn't matter. By the mid-1996s, dozens of nations had followed suit, filling the atmosphere's edge with new machines. These were crude by modern standards, big metal boxes, limited power, minimal control. Once their missions ended, they were simply left where they stopped working. The idea of cleaning up after them felt absurd at the time. After all, space had no atmosphere, no friction, nowhere for debris to drift. Objects launched in the 196s are still circling overhead today, moving at near the same speed as when they left the pad. Meanwhile, the Cold War poured fuel on the launch mania. Every flight carried not only instruments but pride, and sometimes destruction. Nations tested anti-satellite weapons by blowing up their own spacecraft, scattering fragments that would orbit for years. The 1985 US ASM-135 test, for example, turned a weather satellite into a cloud of shrapnel. The Soviets did the same. No one thought long-term. The priority was dominance. Space wasn't about cooperation. It was about control. When the Cold War cooled, a new race began, this time driven not by ideology but by economics. The rise of commercial satellite communications in the 199s turned orbit into open territory for business. Television networks, telecommunications companies, and later internet providers all wanted their share of the heavens. Launch costs dropped, payload capacity grew, and suddenly every corporation with a vision of global reach had a reason to look up. Satellites stopped being symbols of nations and became tools of commerce. By the early 200s, private companies were setting their sights far higher. Early ventures like Iridium dreamt of global coverage with a few dozen satellites. Then came a new breed, spurred by reusable rockets, smaller electronics, and cheaper manufacturing. The vision changed from a handful of satellites to mega-constellations, hundreds, even thousands, forming vast communication webs linking every corner of Earth. Companies like OneWeb, Amazon's Project Kuiper, and most dramatically, SpaceX's Starlink, sought not just to participate in orbit but to own it. Starlink became the symbol of ambition on a planetary scale, tens of thousands of satellites crisscrossing in low Earth orbit, delivering high-speed internet to deserts, oceans, and remote villages alike. The promise was breathtaking: connect every human being anywhere, anytime. It was called revolutionary, but beneath that promise lay a problem as big as the ambition itself. The low-orbit Starlink and its competitors were already crowded, packed with decades of aging metal. And unlike geostationary orbit, where satellites sit in a relatively stable ring far above Earth, these lower lanes are fast, dense, and dangerous. Early tests of Starlink brought both excitement and alarm. Astronomers noticed bright tracks streaking across telescope imagery, disrupting observations. Space agencies realized that mass deployments would mean constant collision monitoring. But the real concern was what Starlink did. It was what Starlink inspired. Competing constellations multiplied the numbers. Launch after launch, batch after batch, each sending 60 or more satellites at once. Even a small percentage of failures would mean hundreds of derelict spacecraft still in orbit. And with each fragment left behind, the probability of collisions soared. For decades, space operators leaned on the assumption that collisions were rare. They were at first, but statistically it's a numbers game. 2,000 satellites pose little danger, 50,000 create a lottery of chaos. Every launch increases the odds that one failed booster, one defunct satellite, or one miscalculated orbit could trigger a cascade. Despite the warnings, the launches continued, driven by profit, competition, and national pride. By the 202s, humanity had turned orbital space into real estate. Governments auctioned off frequency bands as if selling beachfront property. Startups advertised space as a service. Engineers built rockets at a pace unseen in history. Yet above every launch site and every jubilant countdown loomed an unspoken truth. For all our technology, we still had no way to take out the trash. When a satellite died, it stayed where it was, an inert, high-speed hazard waiting for the next unlucky impact. The irony runs deep. The same innovation that finally made space accessible also made it fragile. Rockets landed themselves back on ships, satellites shrank to backpack size, but none of it addressed the growing junkyard around Earth. The sky had become privatized, commercialized, and filled to capacity. And so the race that began with nations proving their superiority ended with corporations competing for orbital dominance. Each promised connectivity and progress, yet each left a trail of fragments that could outlast civilization itself. We used to look up and see possibility. Now, we look up and see traffic, metal, data, and ambition locked in perpetual motion, orbiting a planet that never learned to clean after itself. But every dream leaves junk behind, and unlike on Earth, in orbit, there's no garbage truck. What the Kessler Syndrome really means. To understand what's happening above us, we need to revisit an idea first proposed nearly half a century ago. In 1978, NASA scientist Donald J. Kessler published a paper that sounded paranoid at the time. He warned that as the number of objects in orbit increased, collisions between them could trigger a cascade, each crash producing debris that struck other satellites, generating still more fragments. Over time, he said, this chain reaction could make entire regions of space unusable for centuries. People laughed off the thought. Space felt infinite. But Kessler's math was merciless, and the decades since have only proved him right. Think of orbit like a high-speed freeway circling Earth, except with no lanes, no rules, and everyone moving 10 times faster than a bullet. A single collision isn't like fender benders on Earth. It's an explosion of kinetic energy. Two metal shells slamming together at nearly 8 kilometers per second become instant shrapnel factories. Each piece, no matter how small, carries deadly momentum. A paint flake at that speed can shred solar panels. A screw can puncture a pressure hull. Thousands of fragments from a single impact spread into a swarm that wraps around the planet within hours. This is the heart of what's now called the Kessler Syndrome, a tipping point where debris density grows faster than we can remove it. Below about 2,000 kilometers altitude lies low Earth orbit, or LEO, the region most at risk. It's where we keep communication constellations, weather monitors, spy satellites, and the International Space Station. It's convenient because it's close, but that closeness comes at a cost. Objects here move in tight bands, and when one explodes, fragments spread through all nearby altitudes. Unlike higher orbits, debris here doesn't stay isolated. It crosses paths with thousands of others. Today, our tracking systems monitor around 36,000 pieces of junk larger than 10 centimeters. But those are the visible ones, the safe ones we can predict. Below that threshold lurk hundreds of thousands of fragments too small to see yet big enough to destroy. Radar can't track them all. The Pentagon's catalog grows by the day, but there's always more unseen than known. Each newly launched satellite joins a crowded ballet, dodging invisible bullets through orbital corridors that grow narrower each year. When Kessler introduced his theory, he imagined it as a distant future risk, a century away, maybe more. What he didn't foresee was the explosion of satellite launches after 2018. SpaceX, OneWeb, and others began deploying constellations by the thousands, packing the sky with hardware. The total number of active satellites more than tripled within 7 years. And each one, if disabled, becomes another potential source of fragments. The balance Kessler described, the line between stable growth and chaotic cascade, looks precariously close. To see how lethal that cascade can be, look back to 2009, when a defunct Russian satellite, Cosmos 2251, smashed into an active American one, Iridium 33. The collision at 790 kilometers altitude created roughly 2,000 trackable fragments and untold thousands more too small to follow. Some of those fragments are still out there 16 years later, crossing paths with the International Space Station several times a month. That single event increased the known debris population in that orbital band by more than a quarter. And remember, that was just 2 satellites. Now multiply that by the tens of thousands operating today. Every year, the chance of collision rises. The European Space Agency estimates that without new cleanup efforts, LEO could reach collision runaway by mid-century. Once that starts, it can't easily stop. Fragments create more fragments. Small impacts grind objects into clouds of metallic dust, which then drift across orbital paths like a fog of razors. Atmospheric drag eventually clears out some low debris, but not all. Some of it can stay for hundreds of years. The simplest way to grasp it is statistical inevitability. The more you launch, the more targets exist. The more targets, the greater the odds that two will meet at precisely the wrong time. It doesn't need malice or error, just mathematics. One collision can raise debris counts exponentially, triggering a feedback loop that continues long after the initial crash fades from memory. That's why the nightmare isn't the first accident. It's the self-sustaining chain that follows. Low Earth orbit's crowding makes it worse. Satellites here travel in similar directions in planes. They overtake and cross each other constantly. Add solar activity, a flare that expands the upper atmosphere and slows spacecraft just enough to alter their routes, and those carefully planned trajectories blur. Imagine lanes of traffic bending and weaving unpredictably, while everyone still travels at 28,000 kilometers an hour. A single deviation can spell disaster for everything nearby. If the Kessler cascade were to fully ignite, the results would be catastrophic. Within days, fragments would pepper the orbital bands used for communication and navigation. The International Space Station would face impossible conditions. Cargo launches would halt. The telecommunications constellations that supply internet, GPS, and weather forecasting would degrade one by one. Humanity would remain tethered to Earth, not by rockets or gravity, but by fear. The sky would still be there, glimmering with sunlight on metal shards, but it would no longer be a highway. It would be a minefield. That's the reality of the Kessler Syndrome. Not an abstract threat, but a chain reaction already brewing. Each new launch dips another stone into turbulent water. Physicists compare it to climate tipping points, slow building, invisible and unstoppable once past the threshold. And like climate change, the hardest part is global coordination. Space is owned by everyone and by no one. Each country operates under its own rules. Each company aims for profit first, cleanup later. But debris doesn't respect borders, and it doesn't wait for budgets. There's a cruel irony here. The more dependent we become on space, the more we risk losing it. Every satellite launched to improve life on Earth, guiding ships, connecting rural schools, forecasting storms, also increases the chance that one day we won't be able to launch at all. That's the quiet terror behind Kessler's numbers. A collision chain wouldn't just destroy machines. It would erase opportunity, trapping our species where it began. Yet amid that fear lies a paradox. The same companies fueling the danger are the ones investing most in solutions. SpaceX, for example, claims to design its satellites for controlled deorbit, promising they'll burn up safely at end of life. And the company funds debris tracking initiatives to anticipate collisions before they happen. On paper, it's cleanup through innovation. But the question remains, can you offset risk simply by building faster than it multiplies? That's the irony worth remembering as we move forward, because the company pushing us fastest toward the edge is also trying hardest to save us. And that chase between creation and repair might decide whether humanity has a future among the stars or remains grounded beneath its own debris. Starlink, the billion-dollar gamble. By the mid-202, when most people thought of satellites, one name dominated the conversation: Starlink. What began in 2015 as an experimental network of just a few prototypes had ballooned into the largest private space project in history. Tens of thousands of spacecraft, all built, launched, and operated by a single company under Elon Musk. The idea sounded elegant, a ringing lattice of small satellites encircling Earth, delivering high-speed internet to every remote corner of the planet. No cables, no cell towers, just orbiting access points blanketing the globe. In principle, it promised connection for the disconnected, opportunity where infrastructure had failed. But behind that vision came a level of orbital saturation no one had ever attempted. Starlink operates in low Earth orbit, between 340 and 550 kilometers up, prime real estate for low-latency data transfer. but also the band most at risk from atmospheric drag and debris collisions. Early filings with the U.S. Federal Communications Commission listed around 12,000 satellites. Then, with demand growing and competition looming, SpaceX filed for permission to launch up to 42,000. For comparison, every government and private entity combined had placed only about 11,000 satellites into orbit since 1957. Starlink alone planned to quadruple humanity's entire orbital footprint in less than a decade. It was bold and risky. Each satellite was small, roughly the size of a dining table, weighing about 260 kilograms. Most of their costs lay not in individual hardware but in the logistics of launching in bulk. SpaceX's reusable Falcon 9 rockets changed the economics completely. A single launch could carry 60 satellites, deploy them in orbit, and return the booster for reuse in under an hour after liftoff. The efficiency was breathtaking. Suddenly, once impossible scale seemed routine, but the speed came with consequence. With every new batch, the skies grew brighter, the radio spectrum more crowded, and the probability of orbital incidents higher. Astronomers were among the first to sound alarms. Long-exposure telescope images began showing white streaks, sunlight glinting off Starlink panels as they crossed the night sky. Observatories struggled to plan around the growing constellations. Some argued this was an acceptable sacrifice for global connectivity. Others saw it as a creeping loss of the heavens. The outcry forced SpaceX to experiment with darksat coatings and redesigned visors to reduce reflection. Still, thousands more were already in transit, filling orbital shells like beads on invisible wires. Yet aesthetic concerns were minor compared to collision risk. To manage a flock that large, SpaceX built an autonomous navigation system powered by onboard ion thrusters and the U.S. military's debris tracking data. If a piece of junk drifted too close, the satellite could move itself. But those maneuvers required constant calculation. Each avoidance burned a bit of fuel, shortened operational life, and multiplied workload for ground controllers. Other operators complained that so many automated adjustments made coordination harder. It was like one driver on a freeway swerving constantly to avoid tiny obstacles. Eventually, everyone else had to adjust too. Then came a demonstration of just how fragile such a vast system could be. In February 2025, during a period of intense solar activity, a geomagnetic storm expanded Earth's upper atmosphere. The thickened air increased drag dramatically, slowing a newly launched batch of Starlink satellites before they reached stable orbit. Within hours, 40 of 49 failed to recover altitude and re-entered the atmosphere. Each burned up harmlessly, but the incident revealed an uncomfortable truth. Even advanced constellations couldn't escape space weather. Nature had swiped away nearly an entire launch's worth of machines in a single day. It was a billion-dollar reminder that controlling orbit is not the same as owning it. For SpaceX, publicly at least, the event was a learning curve. Engineers updated launch procedures, added more propellant margin, and designed software to react faster to atmospheric density changes. They emphasized that the satellites were built to safely deorbit at mission end and wouldn't linger as debris. On paper, Starlink met or exceeded debris mitigation guidelines. Still, the sheer scale made experts uneasy. Even a 1% malfunction rate would translate to hundreds of uncontrolled objects. And history showed that once a satellite fails, retrieval is nearly impossible. Government agencies took note. The European Space Agency reported a surge in automatic collision alerts involving Starlink units, forcing frequent avoidance maneuvers for other operators. SpaceX argued that coordination improved over time and that its real-time communication protocols prevented conflicts. But not all satellites belonged to them. Thousands of older relics still circled without maneuvering capacity, silent threats in random orbits. A single strike between one of those derelicts and an active Starlink craft could spew thousands of shards across the very altitude Starlink depended on. the world's internet might literally puncture itself. Economically, the venture was monumental. Analysts valued Starlink as a $100 billion asset, potentially the most lucrative component of SpaceX's empire, funding future Mars missions. Governments in rural regions bought service contracts. Ships and airlines integrated Starlink terminals. For millions, it was the first affordable broadband connection ever. From that perspective, it looked like progress on a planetary scale. Yet for Orbital scientists, it resembled a high-stakes poker game, betting the functionality of near-Earth space for global coverage today. Competitors only amplified the tension. OneWeb, Project Kuiper, and China's planned constellations raced to catch up. Each wanted its own slice of the radio spectrum, each deploying hundreds of craft in neighboring orbital shells. The result was a celestial traffic jam, densely packed layers of communications hardware circling at slightly different heights. International law offered little clarity on responsibility if things went wrong. If debris from one network struck another, who would pay? Who would clean it? No one had answers, and everyone kept launching. Inside SpaceX, optimism never wavered. Executives pointed to internal models suggesting that even with tens of thousands of satellites, risk remained manageable through autonomous avoidance and constant monitoring. They framed criticism as resistance to innovation, comparing it to early fears about airplane congestion or undersea cables. But seasoned orbital analysts saw a dangerous pattern: scaling first, planning later. The logic followed Silicon Valley's familiar mantra: move fast and fix problems afterward. Unfortunately, in orbit, aftermaths travel at 8 kilometers per second. As of late 2025, Starlink had already launched over 5,000 satellites, with another 10,000 approved. The network delivered impressive performance, particularly across remote regions. Yet behind every success story, the isolated community connected, the ship tracing new ocean routes, lay invisible exhaust, orbital clutter. The higher the count climbed, the thinner the margin for error became. Each new deployment increased system resilience and data bandwidth, but reduced physical resilience in space. And that tension between engineering triumph and environmental peril defines the Starlink saga. It's both savior and suspect, solving one planetary problem while edging us closer to another. The billion-dollar constellation stands as proof that human innovation can blanket the Earth in connectivity and simultaneously wrap it in risk. Because no matter how advanced the software or how sleek the spacecraft, the laws of physics don't negotiate. A single stray bolt can undo 1,000 perfect launches. That's the gamble Starlink represents. The belief that technology can outrun probability, that speed and scale can balance precision. It's the wager of an era where ambition outpaces stewardship. For now, it works. Signals flow, profits climb, headlines praise the breakthrough. But the sky remembers every orbiting fragment, every failed component left circling above. The question isn't whether Starlink connects the world. It's whether the price of that connection will, one day, be the very silence of the skies we depended on to make it happen. The solar maximum strikes back. Late 2025 brought something no engineer could outsmart: the sun's temper. Solar cycle 25 had been stronger than anyone predicted, peaking months ahead of schedule and producing the fiercest flares in nearly 2 decades. It started with a flare classified as X93, an intense pulse of X-rays and charged particles that raced toward Earth in minutes. Within hours, satellite operators received warnings from NOAA's Space Weather Prediction Center. Magnetic storms were imminent, atmospheric drag would spike, and electronic systems could glitch or fry outright. For those managing thousands of low-orbit satellites, it was like watching a tsunami roll in slow motion, yet still being unable to move the coastline. The effect on Earth's upper atmosphere was immediate. As high-energy particles slammed into the thermosphere, the thin air expanded outward, increasing density at altitudes below 1,000 kilometers, right where the majority of operational satellites orbit. Normally, that region is near vacuum, but during solar maxima it swells like a living thing, dragging at metallic hulls and slowing them down. Satellites suddenly found themselves plowing through thicker air. Altitude dropped, orbit decayed, and station-keeping fuel burned faster than expected. Low Earth orbit, already crowded, became turbulent in ways physics textbooks rarely depict. Operators scrambled to boost their fleets. NASA shifted weather satellites a few kilometers up. Private constellations switched to low drag modes, angling bodies to minimize resistance. Yet even minor drag over hours accumulates. A few meters lost per second might not sound like much, but at orbital speeds it means re-entry within weeks instead of years. The smallest victims were university CubeSats, tiny, shoebox-sized missions launched for research. 3 Australian satellites, BinR2, BinR3, and BinR4, designed for 6-month lifetimes, plunged back to Earth after barely 8 weeks. Space weather had erased them faster than budgets could replace them. Those were symbolic losses. The real shock came when a fresh batch of Starlink satellites failed after launch. They'd been released just days before a geomagnetic storm erupted. As the atmosphere ballooned, the new units couldn't climb to their intended orbit. Their ion thrusters, optimized for fine adjustments, not brute force, fought futilely against drag that was 5 times stronger than normal. Ground controllers watched telemetry screens fill with warnings. Within hours, 40 satellites slowed too much and began to spiral downward. Some skipped across the denser air like stones on water before burning up entirely. It was spectacular from ground telescopes, dozens of glowing streaks cutting through twilight, a billion-dollar display of physics over profit. The incident made headlines, but for space weather scientists, it wasn't a surprise. Solar cycle 25 had always promised turbulence. The sun's magnetic field flips roughly every 11 years, unleashing streams of plasma and radiation. Earlier models underestimated its amplitude, assuming a gentle peak. Instead, by 2025, solar activity had surged nearly 60% above forecasts. Dozens of X-class flares erupted within weeks. Coronal mass ejections, massive clouds of magnetized gas, hurtled our way, sometimes merging mid-flight into cannibal CMEs that struck Earth one after another. Every hit thickened the atmosphere, disturbed magnetospheres, and sent geomagnetic currents coursing through satellites, power grids, and even long-distance pipelines. For technicians managing constellations like Starlink, OneWeb, or Capella, the storms became endurance tests. Each time solar wind speed spiked, orbital predictions shifted. Collision warning software spewed false positives as orbits wobbled unpredictably. Autonomous avoidance maneuvers triggered more frequently, sometimes colliding with each other algorithmically. One satellite dodging right while another dodged left into its path. The ballet turned chaotic. And because every maneuver used finite propellant, the cost wasn't just operational. It shortened lifespans and increased long-term debris risk. Space had become weather-sensitive infrastructure, just as vulnerable as power lines during a hurricane. Ground-based observers noticed subtler signs too. Radio blackouts across shortwave bands, GPS inaccuracies of several meters, planes temporarily rerouting polar flights to avoid radiation spikes. These interruptions reminded the world that space weather isn't abstract, it reaches directly into daily life. But above all, they underscored something deeper, our growing dependence on a realm we barely control. In 2024, a single flare might disturb communication for hours. By 2025, with tens of thousands more satellites in orbit, the same flare now had global technological consequences. The invisible environment around Earth had turned volatile. SpaceX engineers publicly described the February storm as a wake-up call. They upgraded drag models, improved predictive algorithms using live solar monitor data, and added more thrust reserve to future designs. Yet mitigation only went so far. You can't negotiate with the sun, you can only react to it. And each reaction consumes resources, money, fuel, and operator confidence. What months earlier had been a routine process of orbital maintenance became constant crisis management. Engineers began using language borrowed from meteorology, strong geomagnetic headwinds, atmospheric swell events, severe radio flux alerts. Orbit itself was being weathered. Meanwhile, other satellites quietly died. Unresponsive CubeSats burned unnoticed. Aging weather probes lost stability. Even the International Space Station felt the drag, requiring repeated reboosts to maintain height. Scientists compared it to a cosmic ocean surge, the atmosphere breathing harder than usual, tides rising tens of kilometers. And just as storms churn up debris on a shoreline, solar surges lifted decades-old fragments to new orbits, altering the paths of junk already circling. The debris field became a stirred pot, mixing old and new material in unpredictable ways. Avoidance maps drawn one week were obsolete the next. The irony clawed at policymakers. Humanity was racing to install tens of thousands more satellites, each launch hailed as a triumph of connectivity, precisely as Earth's environment was demonstrating how fragile that infrastructure really was. Solar maximum wasn't a rare anomaly. It was a natural, recurring heartbeat of the sun, meaning every decade would bring repeats. Unless design philosophies changed drastically, each cycle would erase fleets worth billions. Insurance actuaries quietly revised risk models. Premiums for commercial constellations rose sharply. Investors shrugged, betting on replacement speed rather than prevention. The logic was simple: if some die, launch more. But that short-term pragmatism ignored what scientists feared most: a feedback loop between space weather and orbital congestion. Here's how that loop works. Solar flares swell the atmosphere, causing satellites to decay faster. As they fall, they may collide or fragment. Those fragments, higher and smaller, then encounter similar drag in subsequent storms, spreading the debris belt wider. Each generation of fragments increases atmospheric cross-section and drag further, making subsequent flares even more destructive. It's a natural amplifier, one that could push orbital infrastructure to its own tipping point long before true Kessler cascades ignite. The sky, in this sense, is self-correcting through destruction. The more we add, the more the sun strips away. In response, governments reinvested in space weather forecasting. Satellites like GOES-19 and the Parker Solar Probe fed real-time data into predictive AI models. ESA's Solar Orbiter mapped active sunspot regions weeks ahead, giving operators time to postpone launches or change altitudes. Yet despite improved warnings, avoiding drag entirely proved impossible. The atmosphere breathes, gravity wins. Every flare still deepened the sense that our new orbital economy rests on volatile ground, or rather, volatile vacuum. By early 2026, analysts estimated that solar activity had shortened the operational lifetimes of low-orbit satellites by nearly 10% on average. That might not sound catastrophic, but it translates to thousands of premature deorbits and millions more dollars spent replacing hardware. For mega-constellations, replacement is built into the model. For smaller players, it's ruin. The sun had quietly become the regulator of orbital capitalism, imposing rent through radiation. When you look at it that way, solar maximum feels like nature's audit, a reminder that even above Earth, we play by stellar rules. Every pulse from our parent star reshuffles the deck of human technology circling beneath it. Operators can fight gravity, shield electronics, and model drag, but they can't outsmart chaos forever. The same fire that made life possible now tests the machinery that carries our ambitions skyward. And as the sun blazes through the rest of its cycle, the question grows sharper. How much punishment can our orbital empire endure before it burns itself out? Falling dominoes in orbit. It starts with a blip, a minor alert, maybe buried in the middle of a control room dashboard, an automatic collision warning that a satellite will pass within 200 meters of another piece of debris. Operators glance at its sigh and type a command to shift orbit slightly. It's routine now. There are thousands of these alerts every week. But somewhere above, in the silence of low Earth orbit, all those minor adjustments add up to a nervous dance of machines, threading a minefield that gets tighter every day. Real near misses happen all the time. In 2024, ESA's Earth observation satellite Eolus had to move aside to avoid a Starlink craft. Months later, a pair of weather satellites came within less than 50 meters of each other, a speck of distance at speeds of 28,000 kilometers an hour. Even small fragments can trigger alerts. Operators in Colorado Springs track over 1 million potential conjunctions monthly, most resolved automatically, some hair close. The effort is relentless. One outdated Russian rocket stage, a few bolts drifting from an old mission, and the entire global network turns skittish for days. Every collision ever recorded left its mark. The one everyone remembers is still Iridium 33 versus Cosmos 2251 in 2009, the first time two full satellites slammed head-on. The energy released equaled 2.5 tons of TNT, scattering more than 2,000 measurable fragments. That event alone forced hundreds of orbital adjustments over the next decade. Then came smaller strikes. A French military satellite hit in 2013, a Chinese weather craft cracked by an unknown object in 2021, dozens of CubeSats shredded since. The aftermath of each impact isn't just debris, it's statistical poison. Every new fragment multiplies the odds of yet another impact. Tracking networks have improved, but the scale is overwhelming. Ground radar can see objects down to 10 centimeters. Everything smaller is invisible. Yet those millimeter-sized shards are the real killers. They zip through orbital space like sand in a storm, too small to detect but fast enough to pierce shielding. The U.S. Space Surveillance Network issues daily lists of potential conjunctions, while AI models crunch probabilities in real time, ranking threats from ignore to move now. The result is a ballet choreographed by computers, human oversight reduced to approving commands the software already wrote. Still, prediction isn't perfect. Even a half-millimeter error in orbital data can mean hundreds of meters off within a few orbits. In the void between known and unknown lies catastrophe. Take October 2025, when a derelict rocket body drifted near a cluster of imaging satellites. Sensors predicted a near miss. 5 minutes later, radar refinement showed an overlap trajectory. Controllers triggered emergency burns. 2 satellites dodged successfully. One lost contact briefly as solar panels folded too late, and another reported a puncture that reduced power output by 50%. No explosion, no headlines, but a tiny wound that might one day grow lethal. That's how orbital disasters build, incrementally, invisibly, piece by piece. Space agencies have a name for this feedback effect: collision cascading. Each event adds debris. Each new object increases collision likelihood, just like flammable dust thickening in an enclosed room. The 2009 collision added roughly 2,000 cataloged pieces, but years later analysts estimate more than 100,000 micro-fragments still untracked from the same incident. Each passes the globe every 90 minutes, sweeping through altitudes used by everything from Starlink to weather sensors. They don't vanish, they just spread thinner, forming a halo of risk. Avoidance maneuvers now occur daily on almost every major constellation. In 2022, ESA logged over 1,600 such operations, more than double a decade earlier. By late 2025, internal reports suggested nearly 3 maneuvers per satellite per year on average. Multiply that by 20,000 satellites and you get a picture of a sky constantly twitching, each move a toe tip away from chaos. The margin for error is vanishing. When 2 satellites maneuver simultaneously, coordination becomes a paradox. Whose AI moves first? Starlink's system uses predictive paths. OneWeb's reacts to broadcast updates. If latency delays an update by even 1 second, paths can cross instead of diverge. Operators maintain hotline lines between companies to prevent that exact scenario, but sometimes responses overlap anyway. Picture two drivers swerving instinctively in the same direction during a near crash, avoidance that becomes collision. In orbit, there's no honking, no braking distance, just instant decisions and permanent consequences. The sky above looks placid from here, yet every second thousands of metallic bodies pass within distances a crow could fly in a heartbeat. Each of those encounters carries kinetic energy far greater than explosives. The odds of catastrophic impact for any single satellite might seem small, perhaps 1 in 10,000 per year, but with tens of thousands active, probability becomes inevitability. The law of large numbers doesn't care about mission objectives or brand names. Something will hit something, somewhere soon. And when it does, fallout doesn't stay local. A smashed satellite spews fragments outward on slightly varied paths. Because orbital speeds differ subtly across altitude, those fragments spread along a spiral, wrapping the planet in hours. Within a week, the cloud spans entire inclination bands. That's how the 2009 debris ended up threatening the International Space Station years later. Momentum turns wreckage into confetti that never settles. Only atmospheric drag thousands of kilometers below will someday pull it down, and that process can take centuries. Meanwhile, the tracking maps used by mission planners look like tangled webs of colored orbits converging around zones of heavy activity. Analysts privately call them spider nests. Each line represents potential collision corridors. Commercial broadband rings at 550 kilometers, Earth imaging bands at 700, scientific paths around 800 to 1,000. Between them drift hundreds of old rocket stages, propellant tanks, and satellite husks, some tumbling wildly, others frozen in slow spin. The system resembles an overcrowded freeway with abandoned vehicles left in every lane. In response, major agencies and private firms introduced conjunction avoidance automation, trusting machine learning to choose dodges faster than humans. It works mostly, but automation isn't infallible. Algorithms disagree on assumptions, sometimes triggering conflicting corrections. Engineers joke that orbit management now feels like high-frequency trading, rapid, opaque, and one bug away from meltdown. If two networks were ever to feed opposite collision predictions into their fleets, thousands of autonomous maneuvers could ignite simultaneously, a digital panic in space. That may sound extreme, but experts at the European Space Operations Center rate the probability of mass AI conflict as non-negligible. The human cost so far is hidden behind data tables and risk charts, yet the implications are enormous. Every defensive move burns fuel, shortening mission life and increasing replacement frequency. More replacements mean more launches, each producing extra debris from boosters and fairings, a loop feeding itself. Economists compare it to an ecological collapse, too many species competing for finite habitat, degrading it until none survive. The harsher truth is structural. Space activity relies on a stable orbit environment that our own activity steadily destabilizes. The Kessler chain reaction isn't just theoretical anymore. This is its prelude. Each near miss is a domino wobbling in slow motion, not yet fallen but already leaning. We rarely notice because fragments are invisible and time between events feels long. But in orbital terms, human history is a flash. Another decade at current launch rates could double active satellites, turning today's background risk into tomorrow's inevitability. The 2009 crash was the warning shot. The next might be the spark that sets the chain fully in motion. Once that happens, we lose control. The orbital debris web will feed on itself, reducing safe altitudes one after another. By then, avoidance won't help. Every trajectory will intersect danger somewhere. Launching fresh satellites will mean throwing money uphill into chaos. And eventually, access to space, the foundation for whether data, navigation, global internet, and exploration, will narrow to the point of impossibility. Already, engineers speak of clean lanes, the way sailors once spoke of safe passages through reefs, temporary corridors cleared by luck and constant monitoring. The question hovering over every control room is whispered but inescapable. How many dodges before we run out of sky? Because when satellites begin dying faster than we can replace them, the heavens don't go dark all at once. They flicker, system by system, until the network above collapses into silence. That's what scientists call the next threshold, a junkyard in motion, where every piece left aloft becomes both result and cause of destruction. And once the dominoes start falling, there's no reaching up to stop them. 823 words. The hidden cost of losing orbit. When people think about satellites, they often imagine them as conveniences. GPS directions, live news broadcasts, maybe internet in the middle of nowhere. But orbit isn't just a convenience. It's the backbone of the modern world. Every time we unlock a phone, check the weather, fly a plane, or buy something online, invisible signals flick between orbiting machines above and stations on the ground. Right now, nearly 70% of humanity relies on those transmissions in some form. And that's what makes the prospect of losing orbit so unsettling, because it's not just a scientific problem. It would be an economic collapse on a scale the planet has never experienced. Start with timing. Almost every critical network, financial, energy, transportation, depends on the atomic clocks aboard global navigation satellites. Banks use them for transaction timestamps. Power grids use them to synchronize load balancing. Stock exchanges literally cannot match trades without GPS timing pulses accurate to billionths of a second. Remove those satellites and the whole digital economy drifts out of sync. Within hours, transactions fail. Within days, markets freeze. It's not science fiction. Timing outages have already caused small-scale chaos when satellites briefly malfunctioned. Multiply that by a complete orbital shutdown, and you get a global blackout of logistics, finance, and communication. Navigation would vanish overnight. Commercial aircraft plot courses through satellite coordinates. Ocean freight relies on them to cross invisible routes through international waters. Ground-based systems still exist, but they're skeletal backups, not capable of handling worldwide volume. Ships would slow or reroute, planes grounded or forced to navigate by radio and radar, as in the 197s. Supply chains that depend on just-in-time delivery would seize up almost instantly. Then there's agriculture. Precision farming uses satellite imagery and GPS-guided machinery to optimize everything from irrigation to fertilizer delivery. Remove that system, and food production reverts to pre-digital efficiency levels. A single crop season without reliable satellite data would mean smaller yields, higher costs, and shortages across poorer regions first, and no country grows food in isolation anymore. Global grain and cargo markets run on satellite telemetry. Knock those sensors out, and insurance rates and shipping margins skyrocket. Prices ripple through supermarkets weeks later. Meteorology takes an even harsher hit. Every weather forecast beyond 24 hours relies on orbital observations. Cloud motion, sea temperatures, atmospheric pressure profiles gathered from space. Lose those inputs and the predictive models collapse. Hurricanes arrive without warning. Air traffic faces unforecast turbulence. Drought monitoring fails. Disasters grow deadlier simply because we can't see them coming. Communications would fracture, literally. Around 68% of the world's population uses satellite-based internet or telecommunication at some point in their data chain, either directly through constellations or indirectly through backbone links connecting undersea cables to ground relays monitored by orbiting systems. If low Earth orbit becomes unsafe, we lose much of that. Remote regions, entire continents in some cases, go offline. Even urban areas dependent on satellite relay for global connectivity feel the strain as backup routes overload. You might think terrestrial networks would catch the slack. They can't. Fiber runs through limited corridors, vulnerable to disruptions. Satellites fill the gaps between continents and across oceans. Remove them, and the modern internet shrinks into disconnected islands. Streaming services vanish first, but then so does international commerce. Even rescue coordination for natural disasters depends on satellite relays now. A single major debris chain reaction could roll back communication capacity by decades. Energy systems aren't spared. Electrical grids across continents use satellites for synchronization and storm monitoring. Oil rigs, offshore wind farms, mining operations, all rely on satellite telemetry for navigation and remote operation. In a widespread orbital shutdown, maintenance crews would lose positioning data and sensor feedback. The short-term result, localized blackouts. The long-term one, collapsing infrastructure as unmonitored systems fail without oversight. Healthcare feels the fallout almost immediately. Air ambulances, medevac flights, and cargo drones rely on GPS. Hospitals depend on accurate time coding for patient data. Telemedicine, now a lifeline for rural and post-disaster areas, hinges on broadband links delivered from orbit. Without satellites, pharmaceutical supply routes slow, vaccine storage logistics falter, and emergency coordination breaks down. It sounds abstract until you imagine doctors without data, or maps flying blind across weather they can't forecast. Military and defense capabilities crumble too. Surveillance, reconnaissance, and secure communication satellites form the nervous system of national security. If space becomes impassable, missile warning networks go blind. Ground forces lose navigation and targeting support. Even detecting threats becomes guesswork. That vulnerability doesn't stay contained to superpowers. It cascades into tension, misunderstanding, and potential conflict as nations lose situational awareness. In short, an orbital lockdown doesn't just stall technology, it destabilizes peace. The economic numbers tied to this are staggering. The value of services directly supported by satellites exceeds $1 trillion annually. But indirect dependency, everything satellites make possible, easily multiplies that several times over. Economists modeling a Kessler scenario estimate that the functional value of low Earth orbit could fall to zero almost overnight. Launch costs would surge because rockets couldn't navigate debris safely. Insurance would disappear from the market. Investors would abandon space sectors entirely. For nations staking their futures on satellite communication or observation industries, that means recession on contact. And the ecological side effect might surprise you. Many environmental monitoring systems, deforestation tracking, ocean health mapping, polar ice surveillance, depend on satellites too. Losing them doesn't just stop climate research, it blinds our ability to measure what's happening on Earth itself. The irony would be cruel. The same orbital catastrophe that traps us below the sky would erase our best tools to understand the planet we're stuck on. There's a psychological cost as well. For 60 years, spaceflight has symbolized progress. Watching rockets rise, listening to astronauts' voices echo through static, has been our shared proof of advancement. Imagine a generation growing up told that space is off-limits, not because we never reached it, but because we wrecked the path. Astronauts grounded indefinitely, launch pads silent except for mothballed rockets awaiting safer days that never come. Space becomes myth again, framed behind the shimmering barrier of our own debris. It's not just economic paralysis, it's cultural regression. And yet, even as analysts outline these nightmare scenarios, launches continue. The reasoning feels familiar. Someone else will find a fix. Technology will adapt in time. But technology doesn't solve physics. Debris won't politely deorbit itself, and the orbital environment doesn't have spare capacity waiting to absorb endless expansion. Each new satellite risks joining the very gridlock that could collapse its own network. There's a saying among orbital engineers: we treat space like it's infinite because we aren't the ones cleaning it. The hidden cost of losing orbit isn't paid all at once. It's billed slowly: shorter satellite lifetimes, increased fuel burn, skyrocketing insurance, declining reliability. The economy absorbs those costs invisibly at first, through higher communication prices or delayed flights. But somewhere down the chain, that surcharge reaches everyone. Your GPS drifts a few meters off. Your package delivery estimate stretches an extra day. Your news feed buffers because the relay is gone. Those are the human-scale symptoms of a system squeezing itself toward failure. And once the balance tips, once orbital traffic crosses from manageable to unfixable, the bill comes due all at once. Weather warnings missed, financial networks desynchronized, supply chains tangled beyond repair, not with bangs but with absence. Screens flicker, connections drop, silence takes the place of data. The planet keeps spinning, but humanity's reach stops at its atmosphere. Because when we lose orbit, we don't just lose satellites. We lose the infrastructure of modern civilization. The signals linking continents, the timing that unites industries, the gaze that watches over climate and safety, all vanish into static. Every service that defined the 21st century turns suddenly primitive. And the cruelest irony, the damage would be our doing. No alien invasion, no natural disaster, just billions of tiny shards circling endlessly, each one a reminder that in our rush to control the sky, we forgot how to share it. And yet, despite knowing that risk, we keep launching more. Can technology save us? For once, the question isn't whether we can build, it's whether we can undo. The orbital environment is already contaminated, and the race to clean it resembles a triage operation in slow motion. Engineers around the world are attempting to do something humanity has never done before: reach up into the sky and take back the garbage drifting there. It sounds impossible, catching speeding bullets in a storm of invisible shrapnel, but several teams believe they're close. Their tools aren't nets or magnets. They're robots, lasers, sails, and algorithms, all competing against time. The first civil step toward active debris removal came from Europe. The European Space Agency's Clear Space 1 mission, planned for launch in 2026, will test a mechanical catcher that looks unsettlingly like a metallic squid. 4 articulated arms will reach out to clasp a defunct rocket adapter left behind from a past mission. Then both will plunge together into the atmosphere to burn up. It's not glamorous, but it's proof of principle. A spacecraft designed to die deliberately can show how to clean orbit safely. Success would mark the first controlled deorbit of a large, dead satellite. Failure would just add 2 more wrecks to the orbital heap. The stakes couldn't be higher for a single robotic grab. Other innovators are going for speed over precision. Astroscale, a Japanese-British company, is building small space tugs able to locate, attach to, and push dying satellites downward. Their technology uses magnetic docking plates so that in the future, new satellites can include built-in handles for retrieval. The company's long-term plan is to service multiple pieces per mission: dock, deorbit, recharge by in-orbit refueling, and repeat. It's debris removal as a subscription service, an industrial cleanup cycle meant to match the rhythm of new launches. Then there are the experimenters with non-contact techniques, laser ablation systems that vaporize tiny bits of debris surface, nudging fragments onto decay paths without touching them. Ground-based lasers in Hawaii and Australia are entering prototype tests that use millisecond pulses to alter orbits by a few meters per second. It sounds negligible, but repeated exposure effectively lowers debris altitude until it re-enters the atmosphere. Critics worry about dual-use potential. Any laser powerful enough to deorbit junk could also target active satellites. But supporters argue that controlled networks could manage power safely under international oversight. To complement removal, engineers are also designing satellites that remove themselves. Drag sails and electrodynamic tethers, thin, conductive ribbons that interact with Earth's magnetic field, can slow spacecraft naturally at end of life. As the sail or tether deploys, it increases drag, ensuring the craft burns up within 5 years instead of drifting for decades. Some universities already mandate these devices for CubeSat projects. It's the orbital equivalent of a biodegradable bottle. Once used, it dissolves cleanly. Underlying these physical technologies is a quieter revolution in algorithms. The new heroes of orbital safety aren't astronauts but data scientists. Machine learning models now absorb positional data from radar, telescopes, and onboard sensors to predict conjunctions days in advance with precision down to millimeters. AI systems developed by firms like Spaceflux and Paladin categorize debris threats by probability, automatically scheduling avoidance maneuvers across fleets. They can process millions of orbital updates per second, something manual control teams could never do. But it's a paradox. The same automation that allows us to dodge danger also makes the dance denser. Every time algorithms adjust orbits en masse, they reshape the traffic landscape for every other operator. The world's fleets are learning to improvise in real time, guided by computers that sometimes compete as much as they cooperate. Money, surprisingly, isn't the main hold-up. The global space debris removal market is already worth over $1 billion and expected to at least triple by 2003. Governments see an opportunity. Subsidize cleanup now and preserve trillion-dollar industries later. ESA, NASA, and Japan's JAXA all fund demonstration programs, while private outfits pitch the work as green infrastructure, the orbital version of environmental restoration. For once, technology and economics seem tentatively aligned. But the gap isn't technological, it's legislative. International law still defines objects in orbit as sovereign property of the launching nation, even if they're dead. That means a private company can't legally grab a defunct satellite without permission from the country that launched it, permission often complicated by military secrecy. Engineers may be able to catch debris. Lawyers can't agree who's allowed to touch it. This bottleneck has slowed collaboration more than any mechanical failure. Still, incremental progress is happening. The United States Office of Space Commerce, the United Nations Committee on the Peaceful Uses of Outer Space, and various national space agencies have drafted new guidelines for end-of-life compliance. ESA shortened the so-called 25-year rule down to 5, requiring satellites to deorbit within that window or prove a 90% chance of doing so. It's an admission that voluntary measures haven't kept pace with reality. Future commercial approvals may depend on cleanup guarantees, much like automotive emission standards. Governments are quietly preparing for mandatory orbital stewardship. All this momentum hints at a shift in mindset. For the first time since Sputnik, humanity is treating space not as wilderness but as workplace, one that demands maintenance. Ongoing on-orbit servicing missions will soon not only refuel satellites but drag away those beyond repair, blending life extension with waste management. Companies pursuing both goals describe it as orbital circular economy, a phrase that would have sounded absurd a decade ago. Yet it reflects a fundamental understanding. Sustainability won't come from regulation alone but from profit-driven necessity. If cleaning space earns money, it will happen fast. The challenge is scale. Each demonstrator removes 1 or 2 large pieces. Meanwhile, thousands of new satellites launch yearly. The math doesn't balance. Analysts estimate we'd need to eliminate at least 100 high-risk objects annually just to keep debris levels stable. Anything less and growth outpaces removal. The technology works. The clock is what's unforgiving. Every delay means more collisions, more fragments, more targets in need of capture. It's like draining a sinking ship with a teacup. Optimists argue that convergence will help, that a combination of AI prediction, automated servicing, and passive deorbit technology will collectively stabilize the system by the early 203s. Pessimists counter that harmonic coordination across thousands of satellites and nations is a fantasy. Both views may be right. Humans rarely act perfectly, yet incremental solutions often arrive just in time. Perhaps that's the real answer to whether technology can save us. It depends on how quickly we let it act. Progress is no longer about building higher rockets, but about learning humility, treating orbit as finite terrain needing repair. The future may see constellations of cleaners chasing constellations of communicators, perpetual motion of creation and destruction in near-Earth space. It won't look elegant, but neither does survival. And yet, amid the optimism, one question lingers. If every company waits for someone else's system to start the cleanup first, who actually moves? The sky may end up governed by good intentions and stalled implementation. Humanity now possesses machines that can vacuum itself, robots sophisticated enough to undo our mess. But power without permission achieves nothing. History suggests we act decisively only when disaster strikes. Maybe it will take another collision, something visible, undeniable, to transform guidelines into enforcement. Or maybe the sight of clear spaces, robotic arms clutching old debris, will be enough to shift culture from exploitation to care. The tools are ready, hovering in clean room labs and manufacturing bays, waiting for the countdown. So can technology save us? In theory, yes. In practice, only if politics and patience give it room to work. The heavens don't clean themselves, but now, for the first time, they might not have to wait centuries for gravity's help. The machinery of redemption is on the launch pad, engines humming, contracts signed. The next question is simpler and far harder. Will we launch it in time? Power, ambition, and denial. If there's one thing rarer than a clear night sky, it's restraint in human ambition. Space has always been the mirror of our desire to conquer what's beyond reach. But ambition isn't evil, it's survival dressed as progress. The real problem begins when ambition meets denial, when those shaping humanity's future refuse to admit that progress itself is becoming a threat. Every plan for the next decade in orbit reflects this tension. The hunger for expansion balanced against the quiet knowledge that too much of it could destroy the very environment that makes it possible. From the outside, the space race looks more cooperative than ever. Public-private partnerships, global connectivity missions, international data sharing. Behind closed doors, it's driven by competition and fear of being left behind. Every nation wants its own constellation. The United States pushes Starlink and Kuiper. Europe funds OneWeb as a partial counterweight. China develops a sovereign network under its satellite megaplan known as Guoang. Each claims peaceful goals, but the undertone is unmistakable. Orbital control equals political leverage. Whoever commands the skies above Earth commands the next century of information flow, surveillance, and defense. That logic is irresistible and deadly. When agencies gather at international conferences, they talk about orbital sustainability, share pretty infographics, and announce joint pledges. Yet every participant leaves the table planning more launches. That's denial at a structural level. No one wants to blink first, because admitting restraint could be read as weakness. Executives in Silicon Valley pitch expansion as inevitable. Policymakers echo innovation mantras to justify budgets. It's progress as public relations, where the applause drowns out the quiet warnings from engineers pointing at risk curve graphs climbing into the red. This denial runs on psychology as much as economics. To admit that we might already be overloading orbit is to undercut decades of optimism the space industry depends on. Investors hew to positive narratives. Mission planners depend on funding cycles that reward big milestones, not cautious pauses. Admitting a problem means confronting the possibility of regulation, something every commercial operator dreads. So the easy route is selective blindness. Highlight success, downplay collision statistics, frame near misses as proof that safety systems work rather than evidence that danger is constant. What makes this worse is how nationalism amplifies corporate ambition. Every rocket launch sparks patriotic headlines, another step for one nation's technological leadership. But those celebrations create implicit pressure. If one country slows its launches, another will fill the gap. Space doesn't wait. It's treated like a racetrack that closes once someone takes the lead. That's how denial becomes policy, through fear of falling behind. The same dynamic once fueled nuclear escalation. both sides piling missiles because neither dared stop first. Behind the optimism is a quieter community of experts counting probabilities. Orbital analysts at agencies like ESA, NASA, and the U.S. Space Force quietly publish risk models predicting that if satellite growth continues unchecked, collision rates could double within a decade. The implications are financially staggering. Hundreds of billions in lost hardware and insurance shortfalls cascading through global markets. Some economic models suggest global GDP could shrink by 1 to 3% in the decade, following an orbital shutdown. Trillions erased simply because signals can't cross space safely. Yet such predictions rarely reach front pages. They're buried in technical journals or policy briefs that no investor wants to quote during a funding round. And then there's the icon at the center of it all, Elon Musk. Depending on who you ask, he's either the savior of planet-wide internet connectivity or the architect of orbital chaos. Musk's public statements oscillate between reassurance and defiance. He argues that Starlink satellites are designed to deorbit automatically, that collision risks are much lower than people think. That innovation inevitably outpaces regulation. Critics see a pattern of downplaying, the same Silicon Valley belief that exponential growth can solve problems faster than it creates them. When astronomers protested the impacts of bright Starlink trains on telescope images, Musk promised fixes. When debris experts complained about overcrowding, he cited autonomous avoidance. There's always a technical answer, never a strategic pause. To pause would imply uncertainty, and uncertainty is bad for stock prices. NASA officials walk a careful line, praising reusable launch technology while warning that mega-constellations add complexity faster than safety measures evolve. ESA leaders urge tighter licensing but lack enforcement power. The United Nations issues gentle resolutions about long-term sustainability, which have no teeth. It's an uneasy dance where everyone agrees in principle to curb risk, but waits for others to act first. As one European delegate once muttered off record, "We all know the problem. None of us owns the broom." Economically, it's easy to see why denial wins. The space economy is booming, worth over $500 billion and projected to double within a decade. Launch costs drop yearly. Each new technology demonstration opens additional markets: Earth imaging, broadband, climate analytics, defense contracts. There's no incentive to slow down. The public loves space stories. Politicians see them as proof of scientific vitality. Slowing launches to clean up orbit feels like telling people to stop printing money for their own good. So the warnings stay abstract until a crisis provides pictures dramatic enough to break through denial. Some experts compare today's attitude toward orbital congestion to early warnings about climate change in the 197s, data ignored until evidence became catastrophic. The parallels fit uncomfortably well: invisible buildup, global commons, exponential growth, and delayed consequences. Debris accumulation, like carbon accumulation, follows compounding curves. By the time effects become obvious, the damage is largely baked in. We might already be living past the orbital equivalent of 2 degrees warming. We just don't know it yet because orbits decay slowly and statistics lag behind reality. There's another layer too: moral fatigue. Humanity faces so many crises, climate, energy, inequality, that scolding people about invisible junk in space feels abstract. Even when headlines warn of collision near misses or lost satellites, public attention drifts within days. Without pressure from below, governments feel little urgency from above. Space remains romanticized as infinite. The idea that it could fill up feels counterintuitive, but the numbers don't lie. At current rates, tens of thousands of new objects will join orbit this decade, while active removal might capture a few dozen. That ratio defines denial perfectly. Inside control rooms, the mood is both awe and anxiety. Engineers stare at fleets they built and feel pride mixed with dread. Each successful launch represents progress, yet each adds one more variable to an equation edging toward chaos. Some admit privately that the industry is locked in a prisoner's dilemma. If any single actor slows down, others will outcompete them. The only escape is collective enforcement strong enough to hold everyone equally accountable. Right now, such enforcement doesn't exist. The treaties written in the 196s never imagined a private company operating tens of thousands of spacecraft. The legal framework is archaic, the ambitions are futuristic. And so denial persists, not because people are stupid, but because incentives favor it. Corporations profit from launches, governments profit from national prestige, and consumers benefit from cheaper connectivity. The costs are invisible and delayed. That's politics in microgravity, everyone rationalizing short-term gain over long-term survival. Meanwhile, analysts quietly model worst-case events, a chain reaction beginning in the 550-kilometer altitude band, the same lane Starlink favors, propagating outward until all low orbits become lethal. Their economic loss projections exceed $20 trillion globally. Energy grids out of sync, flights grounded, communication crippled. Yet budgets keep approving more launches. Numbers lose meaning when denial becomes policy. Trillion-dollar losses sound like fiction until the lights flicker. Musk dismisses apocalyptic talk as overblown, reminding audiences that his goal is to make life multiplanetary, an escape plan written in corporate mission statements. The irony, critics note, is painful. Building thousands of satellites that might one day trap humanity on Earth, all in the name of ensuring humanity can leave Earth. His confidence feeds followers, irritates regulators, and fuels the cult of inevitability around technology. If progress is destiny, why bother with restraint? But every empire built on that logic ends the same way, believing it can't collapse until the moment it does. And then nature joined the conversation. The solar storms of 2025 didn't care about rivalries or denial. They reminded everyone that physics rules this domain, not politics. For a moment, solar flares shredded the illusion of control. Engineers from every nation faced the same data spikes, the same lost satellites, the same dread. It was as if the sun itself issued a warning. The universe doesn't negotiate with ambition. The question is whether we took that sermon seriously. Because buried inside that storm was a glimpse of our future, a sky that fights back, not out of malice, but out of simple, inevitable consequence. The day the sky closes. It began like any other day in orbit, routine pings from satellites, stable telemetry, controllers sipping coffee in quiet mission rooms. Then a message appeared on a radar console in Colorado Springs, multiple impact alerts at 550 kilometers altitude. Within seconds, more alarms joined. Collisions, plural, not simulated, confirmed. Somewhere above South America, an old rocket body had struck a defunct communications satellite. The kinetic energy equaled several tons of TNT. Thousands of fragments burst outward like invisible shrapnel, each fragment a bullet with global reach. At first, no one understood the scale. Computers mapped debris trajectories, drawing red arcs that multiplied faster than analysts could count. Within half an hour, one of those arcs intersected a functioning Starlink satellite over the Atlantic. Contact lost. Minutes later, 2 more went silent, then 5. Screens filled with static. Operators recalculated orbits and realized something terrifying. The fragments weren't dispersing randomly. They were intersecting the most crowded altitude band on Earth. The cascade had begun. Onboard cameras from a surviving satellite captured brief flashes, harmless at first glance, glints against blackness, but each flare marked another strike. Fragments smaller than pebbles sheared through aluminum panels, antennas, and batteries. A chain of micro-explosions spiraled outward as solar panel shards became new projectiles. Communication between networks faltered. Collision alerts flooded control centers worldwide, thousands at once, too many to manage. Algorithms gave up trying to predict safe paths. Every direction upward became risk. The sky was closing. The first domino to fall publicly was navigation. GPS satellites in medium orbit weren't hit directly yet, but ground relays depending on lower orbit stabilization began malfunctioning. Airliners crossing oceans reported loss of positional accuracy. Pilots switched to inertial navigation and voice radio. Air traffic controllers rerouted traffic. Within hours, global flight maps bled red with delays. Ships crossing the Pacific drifted miles off course. The world beneath the storm didn't know it yet, but civilization's invisible nervous system had started to short out. Above, the International Space Station received its own warning. One fragment cloud, traveling 10 kilometers below its altitude, was projected to rise due to atmospheric oscillations from solar disturbance. The crew sealed hatches and retreated to the docked capsules, ready to evacuate if shattered panels increased cabin pressure risk. Ground control calculated there was no safe window for reboost. Launching rescue craft would mean threading through debris clouds on trajectories already littered with high-speed metal. For the first time in human history, astronauts looked down at Earth and realized they might never go home. Meanwhile, ground stations tried to contact remaining satellites. Many responded with garbled telemetry, some spun uncontrollably. Automated deorbit commands failed as communication networks crumbled. In the following hours, half of Starlink's operational fleet went offline. Their disappearance created new hazards, uncontrolled masses tumbling through the same orbits their siblings still occupied. Bright streaks began appearing above night skies around the world, dozens at first, then hundreds, burning fragments re-entering in fiery arcs. Social media lit up with videos captioned "meteor shower," unaware it was humanity watching its own machines die. Across continents, internet connectivity flickered. Remote towns and ships went dark first, then major hubs felt delays. The redundancy designed into networks couldn't handle simultaneous orbital loss. Data routed through submarine cables overloaded. Banking transactions queued for hours. Airlines grounded fleets. Stock exchanges froze algorithms to prevent cascading errors. Governments activated emergency communication protocols. By dawn, the realization settled. This wasn't a temporary outage. The backbone of the modern world had snapped in the quiet vacuum above. In laboratories, scientists watched decades of equipment perish. Earth observation satellites, those that tracked deforestation, ice melt, and crop yields, were gone. Weather forecasting reverted to pre-space accuracy. Meteorologists reverted to balloons and ground radar. Ocean buoys lost relay, cutting climate models off from data. Space agencies suspended launches. Even sounding rockets risked impact on ascent. The sky had turned from pathway to prison gate. By day 3, the debris swarm encircled the planet, an artificial ring reflecting sunlight into eerie patterns at dusk. Amateur astronomers described it as a ghost belt, shimmering where constellations once shone clear. Governments posted advisories against private launches. Insurance markets collapsed overnight. No policy could cover billions lost in orbit. Engineers downloaded final telemetry of dying satellites, their data streams fading one by one like heart monitors in flatline. Inside mission control rooms, silence replaced chatter. Displays went dark except for persistent red warnings scrolling across them. Collision confidence 99%. Some stations switched off radar to conserve power. There was nothing left to track, just endless fragments chasing one another across predictable doom loops. Humanity's machines had turned against themselves through simple Newtonian inevitability. Each collision spawned hundreds more, each new fragment feeding the storm. Weeks later, attempts to relaunch minimal constellations failed. Surviving rockets aborted after detecting unmanageable risk zones. Fragments large and small now occupied overlapping orbits from 200 to 1,200 kilometers. The so-called LEO exclusion zone had become real. Space agencies called it temporary. Analysts whispered it could last generations. Without functioning satellites, debris couldn't be precisely mapped. Orbital blindness compounded earthly blind spots. We had sealed ourselves beneath an expanding and invisible minefield. Down here, the world adapted clumsily. Ocean navigation reverted to celestial methods. Remote communities lost global communication entirely. Broadcasters signed off channels with messages of apology. We'll be back when the sky clears. But the sky wouldn't clear for centuries. National governments scrambled to re-establish ground networks using balloons and long-range radio. Economies shrank overnight as digital trade routes broke apart. Banks limited transactions to daylight hours when signal interference was lowest. A digital silence settled over night time. The most jarring moment came when astronauts aboard the International Space Station transmitted what would become their final message. Through a crackling feed relayed via a surviving geostationary satellite, they described the planet glowing beneath curtains of re-entry fire. Tiny points of light streaked across atmosphere like slow rain. "We can see debris coming in from all sides," one astronaut said softly. "It's beautiful, and it's all ours." Hours later, communication ceased, not from destruction but deliberate shutdown to conserve power until recovery that never came. The station remained aloft, a sealed memorial orbiting inside a cage of its creators. Months passed. The belt of wreckage stabilized into a continuous haze visible even in daylight, a band of sunlight glare wrapping Earth's equator like a scar. Astronomers tried to calculate decay times. Some fragments would fall within years, others within centuries. Too many to count. Future launches, even robotic ones, faced near certain destruction crossing that band. Humanity, for all its technology, had reverted to a one-planet species not by lack of ambition, but by mechanical consequence. Societies learned to exist without the satellite gaze. Nations fell back on analog systems, ground beacons, localized grids, regional weather charts. The renaissance of terrestrial radio bloomed as engineers rediscovered simplicity, but every broadcast carried an undertone of mourning. We had raised empires in orbit and then buried them under our own arithmetic. People began to step outside again, not to stargaze, but to study that ghost belt. It shimmered faintly, a constant twilight ring marking the boundary between possible and forbidden. Children born afterward would grow up never having seen a launch. To them, spaceflight was myth told by grandparents, the way earlier generations spoke of lost cities beneath seas. Humanity had reached for the stars and built a wall instead. Yet even in failure, fascination persisted. Scientists dreamed of future centuries when debris would decay, when gravity and atmosphere might finally cleanse the sky. They sketched reversal strategies, massive magnetic shields, orbital lasers powered from the moon, but all within timelines longer than nations survive. For now, the verdict was absolute. Orbit was off limits. On the final day before global agencies convened to declare official moratorium on launches, a last rocket stood ready on a Cape Canaveral pad, payload empty, mission symbolic. It never lifted. Wind readings showed high risk from drifting debris re-entry. The countdown froze at 10 seconds and never resumed. Reporters recorded the moment. Silence, then the roll of thunder from distant storms. The image went viral on surviving networks, a grounded rocket silhouetted against a poisoned sky. From that day forward, humanity's footsteps pointed only downward. We had harnessed the heavens for connection, commerce, and pride, only to discover that every orbit has its breaking point. And once broken, it locks shut. The day the sky closed wasn't marked by a single explosion, but by millions of collisions too small to see, each one a confession etched in metal. We looked up and saw a mirror, a reflection of our own impatience glittering back. The stars beyond remained untouched, their light filtering through the wreckage of what we'd built to reach them. The fragile path forward. The morning after the silence, governments held emergency summits. The agenda was simple in wording but impossible in scope: how to bring the sky back. No one wanted to admit that it might take generations. The debris belt still shimmered above, unbroken and uncounted. Yet amid the wreckage came a strange clarity. For the first time in a century of spaceflight, unanimity emerged. Orbital space wasn't a frontier anymore. It was infrastructure, and infrastructure needed maintenance before ambition. Experts called for an approach modeled after environmental reforms on Earth. They spoke of orbital stewardship, a phrase that sounded almost spiritual at first. Nations began drafting binding rules similar to maritime law, requiring cleanup responsibility for every launch. The United Nations Office for Outer Space Affairs convened committees to merge old treaties into something enforceable. No longer would dead satellites be abandoned to fate. If you put something up, you were required to take it down. The shift was astonishing. After decades of voluntary guidelines, governments were suddenly willing to legislate the sky. The European Space Agency led early reforms, enforcing its new 5-year disposal rule across all member states and commercial partners. Companies that violated it faced launch bans in European facilities. Within a year, that rule became de facto global policy. Even SpaceX and OneWeb adopted compliance standards higher than regulators demanded. To meet them, manufacturers rushed to design modular spacecraft that could detach propulsion modules for easier retrieval. A few called it reusability for redemption. Engineers, once obsessed with efficiency, learned to think like custodians rather than colonizers. Technology adapted quickly. Astroscale's autonomous cleaners, once luxury experiments, became essential service vehicles. Fleets of robotic tugs began sweeping lower orbits, nudging derelict shells to re-entry paths. Global insurance associations funded their missions directly, reasoning it was cheaper to remove risk than compensate for lost satellites. Even defense departments started contracting cleanup services for decades-old rocket bodies, turning potential liabilities into public relations triumphs. One Japanese mission deorbited 40 tons of debris in under a year, celebrated worldwide as the first large-scale orbital restoration project. But progress wasn't uniform. Some countries hesitated, arguing that mandatory cleanup would slow development. Developing space nations feared being locked out of the industry by cost. The debate echoed old tensions from climate talks, rich nations demanding restraint from newcomers after decades of their own pollution. To solve this, a new system arose, the Orbital Sustainability Fund, a shared pool financed by major powers to subsidize cleanup for emerging agencies. For once, cooperation outweighed posturing. It wasn't altruism. Every country understood that neglect anywhere endangered everyone. With practical cleanup came philosophical reckoning. Space had always symbolized freedom, limitless void, open to all who dared. Now it carried rules, taxes, even quotas. That felt uncomfortable but necessary. Just as air travel matured from spectacle to regulation, spaceflight entered its responsible phase. Launch managers spoke words unthinkable 20 years earlier: orbital carrying capacity, debris budget, atmospheric replenishment rate. They treated Earth's orbital bands like natural resources, with limits that couldn't be ignored. A new generation of students grew up seeing orbital sustainability as standard practice. In schools, simulations replaced myth-making. Children learned that their first satellite launches would include a cleanup sequence by default. Pop culture shifted too. Films about space disasters gave way to dramas about reconciliation, human cooperation after collapse. The fear of being trapped beneath a hostile sky had shaped something rare: humility. Humanity rediscovered not through expansion, but through responsibility. At 203, orbital management resembled air traffic control multiplied by infinity, continuous, precise, and globally linked. Every object above Earth transmitted its trajectory to an open database updated by AI. Collisions didn't vanish, but they dwindled to rare anomalies. Transparency replaced secrecy. Even military satellites, long shielded by classification, shared anonymized orbital data for safety. Trust built slowly, motivated by necessity rather than friendship. For a few fleeting years, humanity managed to keep the heavens orderly. Still, fragility lingered. The atmosphere remained unpredictable, flaring during solar storms that still erased hardware despite preparation. Debris removal lagged behind creation every time new constellations appeared. Economists reminded policymakers that orbital equilibrium wasn't permanent. It required constant investment. Each lapse reopened the risk of cascade. Yet, after near extinction, no one wanted to test fate again. Space had taught its most expensive lesson. That progress without reflection eventually collapses under its own orbit. In those years of rebuilding, a quiet philosophy emerged among astronauts who finally returned above the Kessler scars. They described seeing re-entry flashes below, cleaning drones guiding old wrecks home, a celestial rain of repentance. One astronaut wrote, "Every piece we burn is a confession." Missions became less about pushing distances and more about restoring possibility. Humanity slowly relearned to earn access to the universe it had taken for granted. Public fascination returned differently too. Launch broadcasts no longer focused on spectacle, but on sustainability scores. Metrics like net debris reduction appeared beside payload mass. A successful flight meant not just reaching orbit but leaving it cleaner. It was bureaucracy fused with idealism, the kind of sober pride civilizations adopt after survival. When the first interplanetary mission resumed decades later, its rocket insignia didn't feature a flag or corporate logo. It bore a simple emblem, a ring breaking apart into sparks, symbolizing the barrier humanity had finally begun to dismantle. Of course, scars remained. Entire altitude bands stayed hazardous for centuries. Future explorers planned around them the way sailors avoided reefs marked on antique charts. Every mission carried emergency re-entry contingency in case old debris belts stirred unexpectedly. The memory of that trapped generation lingered in engineering design, political speeches, and art. The ghost belt served as permanent memorial, glinting faintly at twilight, a reminder written across the sky that progress must be cleaned as it's made. And so the fragile path forward wasn't triumph but balance. Humanity learned that maintaining access to the stars required as much discipline as innovation. It meant accepting limitations, building collectively, and trusting cooperation over competition. The orbital environment had turned from battlefield to commons, sustained not by conquest but by care. We learned that stewardship isn't the opposite of ambition, it's its continuation, refined by consequence. Every generation inherits an atmosphere shaped by those before. Now, humankind inherited the one above as well. The dreams that once filled space with reckless creation evolved into guardianship, a new kind of exploration that begins not with lifting off but by keeping the way open. Because if we lose orbit, we don't just lose satellites, we lose the bridge between our world and every world beyond it. That bridge remains delicate, glowing faintly against the dark, waiting for us to cross it wisely this time. The danger wasn't born from malice, it came from momentum. Humanity built its own prison piece by piece, proudly and without pause. The satellites that once promised connection and progress became the very walls of our confinement. Orbit, once our brightest achievement, became our border. The lesson hangs above us still. Progress without foresight devours its own foundation. Each fragment drifting overhead tells the same story, ambition outpacing responsibility. We treated space as infinite, just as we once treated the oceans and atmosphere. But every frontier fills faster than we understand it. Those shells circling Earth aren't relics of exploration. They're reflections of a civilization that never slows until something gives way. The question is no longer whether we can touch the stars, but whether we can repair the distance we've created between them and us. Survival now depends on a simple shift, turning ambition into stewardship. The tools that clutter the sky can also clear it if patience outweighs rivalry. Our next great discovery may not lie on another world, but in learning how to coexist with what we've built above this one. The Kessler warning endures as a mirror. Starlink's story remains its echo. Purpose must travel slower than possibility, or it burns up on the way. Look up tonight. Every moving light across that darkness is both hope and hazard. Each surviving orbit reminds us that humility still has a place among the stars. Humanity's fate isn't sealed under debris. It's balanced on awareness, a fragile thread stretched across velocity and time. The future of the sky will be defined not by who launches most, but by who decides what shouldn't go up at all. Spaceflight isn't just engineering, it's conscience. To keep reaching outward, we must protect the corridor that connects worlds as fiercely as we once pursued the first launch. The responsibility is shared, starting now, with every countdown that echoes across the coast. Because the true danger of the Kessler Syndrome isn't losing orbit, it's forgetting why we built it. To connect, to explore, to prove that understanding could conquer distance. If greed or neglect closes the heavens again, we lose more than technology. We lose the proof that we can grow beyond repetition. Humanity has one sky, one chance to keep it open. It demands caution, cooperation, and quiet courage. The question remains, can we protect the bridge we built before it collapses beneath us? The answer begins every time someone chooses restraint over reward. If you want to see just how close we are to losing the sky, watch this next. Subscribe for more untold cosmic stories and help keep the conversation alive before silence returns above us.